We're starting chapter 7 today. Section 7.1 is on verifying identities. And I want to go back and look at our equation of the unit circle to explain what an identity is. All right, so a long time ago when we introduced the unit circle, we said that the unit circle itself has the equation x squared plus y squared is equal to 1. But then we went further and defined the x and y coordinates to be the cosine and the sine of the associated angle on the unit circle. So because cosine is the x coordinate and sine is the y coordinate, instead of saying x squared plus y squared is equal to 1, we could say that cosine squared plus sine squared is equal to 1. And this actually ends up being true for every angle in the universe. So we could ask Desmos, I could type in cosine of any angle you wanted. So I'm going to make up some kind of funky 5 pi divided by 17. All right. And I'm going to take that cosine and square it. And to that, I'm going to add the sine squared of that angle. So let's scoot my window over so you can see what I'm doing here. All right, so let's do the same thing for sine. So I'm going to take sine of 5 pi over 17. Same thing. And we're going to square that. And it tells me 1, right? And it does not matter which angle you might choose to plug into this little identity here, cosine squared plus sine squared. You could plug in any angle that you could make up, positive, negative, huge, radians, degrees, anything. As long as you put the same angle in the cosine as the sine, you square them and add them together, the answer is always 1. This is an important relationship that sine and cosine have with each other. All right, so that cosine squared plus sine squared being equal to 1 is just one of countless many trigonometric identities that are true about all of our trig functions. They have all these different relationships. So the one that I just showed you is this one down here, sine squared plus cosine squared equals to 1. That's one of the most important, useful trigonometric identities that we have. And notice that I moved that square instead of writing sine theta squared, kind of how we were telling Desmos. We just kind of move that square onto the sine, but that's really what that means. Sine squared plus cosine squared is equal to 1. It turns out there's a Pythagorean identity, tangent squared plus 1 equals secant squared, 1 plus cotangent squared equals cosecant squared. We've got all different kinds of identities. These are just a small pile of them that might be useful. Okay, so we want to have this handout on hand as we go into section 7.1, where we're going to learn some other identities and we're going to prove that those are true by using these ones that we already know. All right, so this is the first example I'm going to do for you in just a minute. We have an identity here. I'm telling you that this identity, tangent plus cotangent, is always equal to secant times cosecant. It's always true no matter which angle you might choose to plug in, 5 pi over 17 or any other angle. It would always work that these two sides of the equation are equal to each other. And we're going to prove that this is true. So this is different than trying to solve an equation. So I'm not solving for x. I'm trying to show that this equation is true no matter which value of x you might plug in. Okay, so how do we do this? All right, so here are some strategies we're going to use when we're verifying identities. This is proving that an equation is true for all values of theta or x, not solving for theta or x. All right, so the first thing we're going to do is that we're going to work with one side of the equation only. So this is not like solving equations where I can add 2 to both sides of the equation. You can only do that when you know that those things are equal. When you're trying to prove that things are equal, you can't assume that and treat it like it's already an equality. So we're going to start with one side of the equation only. And usually this is counterintuitive, but starting with the more complicated looking side is usually easier. It's got more moving parts that you can kind of manipulate and see what falls out. Look for opportunities to use identities. You've got that identities handout that I posted. You can use that as a reference. And the last one is try something, anything. So when you look at these identities, you're not going to know how to verify it just by looking. Nobody knows how to do that just by looking at an identity. You have to try something. You have to see what you can do. So we're just going to apply a bunch of techniques and see what falls out. All right, so I said we were only going to work with one side of an identity at a time, and you need to pick which side, and you need to indicate which side of the identity you've chosen to work with. I'm going to use the left-hand side. I said to use the more complicated side. I don't know if that's more complicated, but that's the one I'm going to go with. So I'm going to write that I'm working with the left-hand side, so LHS, left-hand side of the identity. So I'm going to copy down the left-hand side. And I'm going to use what I know about these trig functions to try to manipulate this to look like secant times cosecant without making up new math rules. All right, so I'm not going to mess with secant times cosecant at all this whole time. I'm just going to leave it up there as inspiration. All right, so my first technique that I could show you for verifying identities is to try to rewrite everything in terms of sine and cosine. So I'm going to write tangent and cotangent in terms of sine and cosine. So I know that tangent is equal to sine over cosine. And I know that cotangent is the reciprocal of that, cosine over sine. All right, so that doesn't quite look like secant times cosecant yet, but don't panic, we'll work on it. All right, so right now those two fractions are adding together, and on the right-hand side of this identity, secant times cosecant, things are multiplied. They're all kind of squished together in one term. So one way that you can squish together a couple of trig functions is to add fractions. All right, so I'm gonna add these two fractions together. Now think, when you're adding fractions, like up here in the right-hand corner, I'm gonna write like 1/2 plus 1/3. You would have to get a common denominator. And to do that, you would think, okay, what's 2 times 3? That's 6, right? So I would multiply this function by 2 over 2 and this function by 3 over 3. All right, so you're kind of multiplying the denominators to figure out the common denominator, and then you're multiplying each fraction by what it doesn't have to create the common denominator. So looking at my sines and cosines over here, my common denominator is just going to be cosine times sine. So I'm going to multiply this function by cosine x over cosine x, just like I would the 2 over 2 on the top right of the screen. And then let me get rid of my equal sign because it's in my way. I'm going to multiply this one by sine over sine. Okay, because now I have sine times cosine and sine times cosine, the same denominator between the two fractions. All right, so look at the first blue bracket there that I have. That first term, I'm going to multiply fractions across the top. Sine times sine would give me sine squared. And on the bottom, I have sine times cosine. My second blue bracket, I have the top times the top. Cosine times cosine gives me cosine squared. And then on the bottom, I have that sine times cosine. Now, notice as I've been doing this, I have not actually had a clear path of where I'm going. You usually don't when you're verifying identities. You're just rewriting stuff without making up new math and seeing if something falls out. And something's about to fall out. All right, so we're going to add our fractions together. We've got the same denominator, so I'm going to copy that same denominator down here, sine times cosine. And add the numerators, so sine squared plus cosine squared. All right, and the numerator of that fraction is what we were talking about over on Desmos. It does not matter what the angle x is. When you square cosine and you square sine and you add them together, the answer is always 1 by identity. This is equal to 1. All right, so what do we have left with that 1 up top? So this is equal to 1 up top. On the bottom, I have sine x times cosine x. All right, and thankfully I have that written right below my inspiration there. I have sine and cosine down in the denominator, and that should look hopeful to you, right? Because secant is 1 over cosine, cosecant is 1 over sine. So if I write this in kind of a clever way, I'm gonna unmultiply these fractions, 1 over sine x and 1 over cosine x. All right, if I were to multiply those two fractions together, I'd get 1 on top, sine cosine on bottom. So I've kind of just unmultiplied that fraction. And then this guy right here is secant. And this gal over here is cosecant. So I've got secant times cosecant, or cosecant times secant, same thing. All right, so now I've shown that what I had on the left-hand side by reworking it is actually equal to the thing that was on the right-hand side. All right, so these verifying identities should look like a mathematical sentence. It starts off at left-hand side, all this manipulation, right-hand side. So unlike solving an equation where I'm looking to see if you got the right answer, here I'm looking to see if your explanation makes sense from start all the way to finish. We'll do a couple more examples in the next video.